Thank you. Thank you for the opportunity to come and give this lecture. This will be kind of my point of view of where we've been with the neutrino oscillation experiments and where we're going with the long baseline experiments, but I hope you'll find it useful. So I just want to start with, I think probably many people here know well the physics of neutrino oscillations and mixing, but I just want to start with a simple introduction to this so we're all on the same page. So neutrinos, of course, interact via the weak force, and they have, they have states of definite flavor that are associated with the charged lepton. So under the charge current interactions, we have the associated charged leptons. But neutrinos also have mass, so when they propagate, they will propagate as states of definite mass. And the flavor states of the neutrino and the mass states of neutrino should be related by some unitary mixing matrix. So if we allow, if we produce a neutrino in a state of definite flavor and allow it to propagate, the mass states will propagate with different phases, and after some distance, we may measure a different flavor composition. So for the 3 neutrino mixing, we parameterize this mixing with the PMNS matrix, which is often parameterized with 3 mixing angles that are theta 1,2, theta 1,3, and theta 2,3, and then 1 phase that can allow for CP violation in the neutrino mixing. I won't talk about it, but there are also additional Majorana phases that can introduce CP violation. So when we consider this unitary mixing matrix and then calculate the oscillation probabilities, we find that they also depend on the mass squared splittings of the neutrinos and of course the distance over which the neutrinos travel and their energy. So we have a general formula for the oscillations in vacuum for the probability for a neutrino to change flavor. Okay, so we have these 3 mixing angles, the CP phase and the mass squared splitting. How well have we measured these things? Actually, now all of the mixing angles are measured pretty well. It's actually interesting if you consider the fractional error on the sign of the mixing angles. It's about the same for all 3 of the mixing angles. But we range from a relatively small mixing through theta 1,3 to essentially what's consistent with maximal mixing, a mixing angle of 45 degrees in theta 2,3. And I'll talk about this more, but experiments are now starting to constrain the CP phase as well. So if we look at global fits of the CP phase, there's now essentially a preference in the global data, which is the blue here, for a value that's close to 3 pi over 2 or 270 degrees, or sometimes we say minus pi over 2 since it's a cyclic parameter. But that would be actually maximal CP violation. But of course, we still need more data to really constrain this. And then finally, we know the delta m squared 2,1 mass squared splitting. And delta m squared 3,2, we have pretty good measurements of the absolute value, but the thing that we don't know is whether this third mass state is the heaviest or the lightest. So we say that's either normal hierarchy or inverted hierarchy. So we want to measure these parameters. Why are they interesting? Well, the neutrino oscillations the parameters that we measure in neutrino oscillations should relate to a high energy theory that tells us how neutrino masses are generated, and how flavor is generated. And in particular, there are kind of hints that there's something interesting going on with neutrinos. So of course, the neutrino masses are much smaller than the other particles in the standard model, and this could be explained by some mechanisms such as the C-cell mechanism. We also see that if we look at these mixing angles and compare them to the CKM matrix that governs the mixing of the quarks, where the CKM is something that looks rather diagonal, that's really not the case for the PMNS. So it's interesting that we see this difference. We're also interested in neutrinos because it's introducing a potential source of CP violation in the neutrino sector, which may give us an explanation of the baryon asymmetry through leptogenesis. Okay, so let me give a bit of a historical perspective on the discovery of neutrino oscillations. I think people here have probably heard of the home stake experiment, which was the kind of first experiment to see something interesting going on with neutrinos. And this was looking at solar neutrinos using a large chlorine detector in the Homestake mine in South Dakota and measuring the neutrino interactions through this process. And you can see this really impressive here. This is a plot extending from 1970 to 1995. All of this data collected over decades essentially showed that about 1/3 of the number of neutrinos were being observed as what was predicted by the solar models. So, of course, one possible explanation for this was that there could be neutrino oscillations happening, but another possible explanation, of course, is that there was something wrong with the solar model. The existence of neutrino oscillations were really pinned down by two experiments that were awarded, for which the 2015 Nobel Prize was awarded. The first of these is Super Kamiokande. So this was by the late 90s, there were observed anomalies in the solar and atmospheric neutrino data that pointed to something going on. And the Super Kamiokande detector was built, it was a large water Cherenkov detector, so 22.5 kiloton fiducial mass. It's still our largest neutrino detector, excluding the IceCube. So what this did was it measured the oscillations from atmospheric neutrinos, but it had enough statistics to look at these oscillations as a function of the zenith angle. So that's essentially as a function of where the neutrinos are being produced in the atmosphere around the globe. So a neutrino coming from this direction has a much longer baseline compared to a neutrino coming from this direction. And what could be observed was that the downward going neutrinos didn't see a significant oscillation effect, but the upward going neutrinos did. So this showed that there was a baseline dependence of this neutrino deficit, which was consistent with oscillations. The other experiment I want to talk about is the snow experiment. So this is a heavy water Cherenkov detector that could actually detect solar neutrinos in 3 different modes. So essentially in the charge current mode, where it was only sensitive to the electron neutrino because production of muon or tau's would be above the threshold. The neutral current mode, where it's sensitive to all flavors of neutrinos. And the electron scattering mode, where it's also sensitive to all flavors of neutrinos, but with different weights than in the neutral current mode. And this is essentially showing the measurement using all 3 of these modes to get the flux of the nu e compared to the flux of the nu mu and nu tau. And what this showed was that yes, about 1/3 of the neutrinos are nu e, and the rest are nu mu and nu tau that we could see through the neutral current and electron scattering modes. So once again, this experiment really showed that this was an oscillation process because we could see that not only was there a deficit in the nu e, but we could see that they were changing flavor to the nu mu and nu tau. So these 2 experiments really proved that neutrinos oscillate, and for that the Nobel Prize was awarded in 2015. Okay, so let's move on to a different type of neutrino experiment, which is a neutrino experiment with a human-made source of neutrinos. And generally, there are 2 human-made sources that we're looking at. Of course, there are reactor neutrinos, and I think people are probably familiar with the measurements of experiments like SHO and Daya Bay and RENO to measure the neutrino oscillations with reactor neutrinos. But also we can produce neutrinos at accelerators. So the way that we do this is we have a beam of protons that we collide with a target, typically some light nucleus like graphite or beryllium target. We have toroidal magnetic horns that can focus the charged particles that are produced in these collisions. So for one polarity we would focus pi plus, for another polarity of the horn we would focus pi minus. And then in the decays of these pions, we can produce what's mostly a muon neutrino or muon antineutrino beam. Now, in all of these experiments, we build near detectors that are located close to the neutrino source, and that's so we can measure the neutrino oscillations, the neutrino rate before the oscillations happen. And then finally, after some long baseline that's measured in hundreds of kilometers, we measure the neutrinos after oscillation. So of course we need a far detector to do that, and it has to be very big to get enough rate to measure these processes. So the nice thing about this type of experiment is it allows us to control the parameters of the experiment that are relevant for studying the physics. So we can control the baseline by building the neutrino source and the far detector at a given distance. We can tune the spectrum for the neutrinos to desired energies based on the energy of the proton beam, but also, as I'll explain, based on the angle between the beam and the far detector. And we can select whether the beam is actually a beam of neutrinos or antineutrinos. So if we flip the polarity of this horn, we focus pi plus or pi minus, and we get neutrino or antineutrino beams. So this really allows us to, and in the combination with near detectors, this really allows us to control the experiment in a way that you can't necessarily with a natural neutrino source. Of course, we need to detect neutrinos in our experiment, and generally we want to do this through the charge current interaction because that gives us the charged lepton in the final state, and we can use that to infer the neutrino flavor. The problem here is that we're detecting neutrinos through interactions on nuclei, and it's not very easy to model this. So the nucleus, of course, we can have coherent scattering on the nucleus, we can have scattering on individual nucleons in the nucleus, we can have deep inelastic scattering, and we have various nuclear effects that change the amplitude for these scattering processes. This nuclear physics also gives us rather interesting final states that include hadrons, so protons, pions, and neutrons in the final state. And what's unfortunate is we don't always detect all of these in our experiments. So for example, in a water Cherenkov experiment, a proton in the final state will typically be below Cherenkov threshold. So we won't detect that particle, and we don't know anything about the energy of that proton. Even for tracking detectors that can track all charged particles, detection of neutrons is still a real challenge, and you don't necessarily measure the energy carried away by neutrons. So this is a challenge for us because we need to reconstruct the energy of the event because the oscillation probability depends on energy. But we haven't measured all of the particles in the event, and it's difficult to model how much of the energy these particles that we haven't detected should carry. So this is one of the real challenges for future experiments, and I'll talk about this later. But the problem that we have is that our models don't necessarily agree with each other, and they also don't necessarily agree with the data. And just to show you that these effects can be rather large, even in a case where we're doing calorimetric reconstruction, where we try to reconstruct all of the particles and see the energy, you can see that the blue curve here shows what you would get in reconstructed energy for a given true energy if you could measure perfectly all of the particles excluding neutrons in the final state. And this red curve shows what you get when you put in realistic effects like the detector efficiency and the resolution of the detector. So you can see that understanding this is really challenging, and going from here to here really depends on what this final state is made up of. So this is a real challenge for our future experiments, and I'll talk about what we do about that later. But first, let me discuss then the history of the long baseline neutrino experiments. So the first generation long baseline neutrino experiments were starting with K2K in 1999. So this was with a neutrino beam produced at KEK in Tsukuba, Japan, and aimed at the Super Kamiokande detector, so the same Super Kamiokande detector that was detecting atmospheric neutrinos, with a baseline of about 250 kilometers. And that was followed then by the Minos experiment with a beam produced at Fermilab. So this is a higher energy beam and a longer baseline for the experiment, so at 735 kilometers. And this didn't use a water Cherenkov detector, but rather a magnetized steel detector with interlaced scintillating panels to detect the particles. Okay, so these two experiments were our first generation, and they were primarily looking at this oscillation probability mode. So this is essentially the muon neutrino or muon antineutrino survival mode. And what we generally extract from this was sine squared 2 theta 2 3 and delta m squared. So the primary dependence in this oscillation probability. This term is small because theta 1 3 is small. So this shows you the spectra observed by these two experiments with MINOS data through 2008, which was before we were turning on the next generation. And you can see what they expected without oscillations and what they observed. So they did observe some deficit, but you can also see that these experiments weren't necessarily tuned very well. The oscillation effect was more at lower energy compared to the energy of neutrinos being produced here. However, it was good enough to really, in the end, pin down the value of delta m squared, which is really important for getting this right choice of the L over E for the experiment so that we can really make optimal experiments to measure the neutrino oscillations. So that leads us to the current generation of neutrino oscillation experiments that are long baseline experiments that are running now. So T2K has been running since 2009, and I'm a collaborator on T2K. And this is an experiment in Japan. So once again, we're using the Super Kamiokande detector as the FAR detector. But now the beam is produced at the J-Park accelerator in Tokai village, which is 295 kilometers away. The other experiment that's running now is the NOvA experiment. So once again, this is an experiment produced at Fermilab with protons from the main injector. And the FAR detector for NOvA is in Ash River, which it has a slightly longer baseline than MINOS. And in this case, the detector is a segmented liquid scintillator detector. And this has been operating since 2014. Okay, so I'm sorry I have to do one slide with a kind of long equation on it, but I think understanding this will help us understand what the current generation and next generation experiments are trying to measure. So this is the oscillation probability for muon neutrinos to oscillate to electron neutrinos, and this is the channel that we're really interested in these days. So if we look at the leading term in this channel for the delta m squared 3.1 or delta m squared 3.2 mass splitting, this is shown here. And this is giving us sensitivity to sine squared 2 theta 1.3, which is also the parameter measured by the reactor experiments, but also sine squared theta 2.3. And this is sine squared theta 2.3, not sine squared 2 theta 2.3. So it gives us sensitivity to the octant of this mixing angle. So this is giving our leading term, giving us sensitivity to those. And then we have these interference terms, and I'll point to the second interference term here. So one point about this is that the sign of this term flips depending on whether you have neutrinos or antineutrinos. And it depends on the sign of this CP phase. So this is the term that introduces CP violation into this oscillation probability. So by this essentially this effect allows us to measure this CP phase. And then finally, in this mode, we can also measure the effect, the matter effect. So essentially, the traveling through Earth produces an additional potential, which actually gives us a sensitivity to the mass ordering. So we can know whether we have the normal hierarchy or the inverted hierarchy. So there's a lot of physics going on in this equation, and even more than what I've talked about here. But these are the main things we're focusing on for the current generation of experiments. So both T2K and NOvA use a technique called an off-axis beam for their experiments to really tune the experiment to make the most sensitive measurement possible. So essentially, this is just a technique that takes advantage of the kinematics of the two-body decay of the pion. And essentially what that tells you is that if you look in the direction of your pion and look at the neutrino energy that you get increases linearly with the energy of the pion. So if we have a beam that's made up of a broad range of pion energies, that'll produce a beam of a broad range of neutrino energies. But as you start looking off the axis from the average pion direction, what you see is that actually this dependence flattens out. So even though the pion energy is increasing, the neutrino energy isn't. And what this gives you is essentially much narrower band neutrino beams. And in fact, we can then design the experiment so that we have this narrow band beam that sits right at the first oscillation maximum and really get the best sensitivity out of the experiment as possible. Okay, so I'll briefly show the results from the T2K and NOvA experiments as they stand now. So the plots that I'm showing here are a useful way to show the results for the neutrino for these experiments where we compare the rate of neutrino interactions in the experiment to anti-neutrino interactions. And these in some way show the sensitivity of the experiment. So you can see these ellipses are the predicted rates for different choices of the hierarchy in red and blue in this case, and in dashed and solid in this case, and for different values of the CP phase. So what you can see in NOVA is that there's a much stronger separation of the two hierarchy hypotheses because of the longer baseline than there is in T2K. As far as what the experiments measure, so this is where the NOVA data lies, and it's essentially having a preference for the normal hierarchy, but no very strong preference for the CP phase. On the other hand, T2K is seeing this kind of fluctuation of the data even away from the predicted values that is preferring a large CP violation effect. So essentially a CP phase that's at -π/2 or 3π/2. In the end, T2K disfavors the CP conservation at about 2 sigma, but that's in part coming from the fact that we see this fluctuation in the data beyond what our typical sensitivity would be. These experiments also measure the mixing parameters, the delta m squared 3.2 and the sine squared theta 2.3 oscillation parameters. In NOVA's case, they have a preference for a value that's away from maximal mixing, which is 0.5 on this plot, whereas T2K's result is generally closer to maximal mixing, but at least these two results are still generally consistent. We'd like to know if maximal mixing is there because in some sense we would think that that would point to some underlying symmetry in the theory that would predict maximal mixing for one of the angles. So for the future, for T2K and NOVA, for the operation is essentially planned to continue for both of these experiments. For T2K until 2026 with near detector upgrade and also a beam power upgrade. And for NOVA until 2024. And these are plots showing some projections of the sensitivity for these experiments. So in this case, this is showing for if the delta CP is at maximal CP violation, essentially what significance T2K would be able to measure CP violation with. And essentially in this program, it can get to 3 sigma if we're lucky and the CP violation is large. As I mentioned before, with the longer baseline, NOVA is more sensitive to the mass ordering, and this is showing their sensitivity to the mass ordering. So if we're in the normal hierarchy and the CP phase is close to what the global preference is now, that's actually where NOVA is most sensitive and could in fact make a 3 sigma measurement of the mass hierarchy if we're lucky to have those values. If we end up at other values, then we may not be so lucky. Okay, so what do we do for the next generation of experiments? So essentially, the T2K and NOVA will be replaced with the improved experiments. In Japan, the planned experiment is Hyper-K, which is essentially using a very similar experimental setup, but building a larger water Cherenkov detector and having a higher power beam. The DUNE experiment is more of a change compared to the NOVA experiment. So in this case, a broadband on-axis beam is being used, and I'll show that later. The baseline is increased to 1,300 kilometers to get more of a matter effect. And a new type of detector is being used, a liquid argon TPC. So there are rather dramatic changes here. Okay. I won't have time to talk about all the physics that these two experiments can do, but I just want to take the moment to point out that it's really quite broad, and it's not just the long baseline oscillation physics. That includes atmospheric neutrino measurements, including tau neutrino appearance, nucleon decay searches, the most sensitive nucleon decay searches in many of the interesting channels, supernova relic neutrino searches, solar neutrino measurements, and of course, these very large detectors will be our best detectors for measuring neutrinos if we are lucky enough to have a nearby supernova. Okay, so let me talk a little bit more detail about Hyper-K. So as I mentioned, we're increasing the beam power. So currently the beam power for T2K is about 500 kilowatts. But the plan is to get to 1.3 megawatt beam power for Hyper-K. And then increasing the size of the detector. So these are actually real models of the original Kamiokande detector, Super Kamiokande, and Hyper-K. So you can see the progression in size here. And Hyper-K with 172 kiloton fiducial mass will give us an 8 times larger fiducial mass than Super Kamiokande. So we'll get 8 times as many events. We're also developing new photo detection technology, which will improve our ability to detect photons, and new near detectors, and I'll talk about one new near detector later. But all in all, we'll be able to accumulate statistics about 20 times faster than we can currently do in T2K. So this data will really open up a new regime. And in fact, after 10 years of operation, we'll have about 2,000 electron neutrino and electron antineutrino candidates each in Hyper-K to make this CP violation measurement. Let me remind you that in T2K and NOvA now we have tens of candidates. So this is really a step up in statistical power of the experiment. But what that means is that we also have, with the statistical power we can really see, so these are statistical error bars as a function of reconstructed energy bins, and we can really see quite clearly the effects of the CP phase. But this leads to about a 3% statistical error on the CP asymmetry that we would measure, which gives us a challenge because we have to control systematic uncertainties to get down to actually better than that level to really take advantage of the sensitivity of the experiment. And T2K is at 6% now, so we really have our work cut out for us. That's a problem that's true for DUNE as well. But anyway, assuming that we can control systematic errors, then we can make really sensitive searches for CP violations. So we can get 5 or 3 sigma sensitivity for the CP phase for 50% of the values or 76% of the values in the 3 sigma case. So we have this broad sensitivity, and we can also start to really pin down the value of the CP phase itself. This is showing the 1 sigma precision for the measurement. Actually, you can see that it's a bit worse at 90 degrees or pi over 2 compared to at 0. And I'll explain a little bit more about that later. The baseline for Hyper-K is rather short, so you might worry that it doesn't have sensitivity to the mass hierarchy. But Hyper-K does have sensitivity to the mass hierarchy through the atmospheric neutrinos, which of course covering a range of baselines. And there will be a very large sample of atmospheric neutrinos collected in Hyper-K over 10 years. So in fact, in Hyper-K, we can also determine the mass hierarchy to the 4 sigma level. Okay, so let me switch to the DUNE experiment now. So as I mentioned, DUNE is a completely new beam, completely new detectors at a completely new site. The beam will still use the main injector protons, but there will be a new neutrino beam line. And as I mentioned, this will be an on-axis beam, which means the energy range is rather broad. So you can see the energy range here. And what that broad energy range means is that DUNE is really probing kind of the full oscillation probability at the first oscillation maximum and even into starting to go into the region of the second oscillation maximum. So this is a unique feature of DUNE. The beam power will be quite high, starting at 1.2 megawatts and later upgraded to 2.4 megawatts. Okay, and I'm not an expert on this, so I won't discuss in much detail the detector technology for DUNE, but I'll just give a brief explanation here. So DUNE will use a liquid argon TPC. So this is a time projection chamber in liquid argon, where essentially ionizing particles produce charge in the detector, and you drift those charges with some large electric field to a readout plane where you can detect a charge. This is actually an event display from the single phase proto-DUNE. So this is a prototype DUNE detector that operated at CERN in a test beam. This is looking at one projection of the event, but you can see here that you get kind of almost a bubble chamber-like a view of events in these liquid argon TPCs. So there's really a lot of information here. DUNE is actually pursuing 2 different types of technology for these detectors. So one is this single phase where the whole detector is liquid argon. Another is the dual phase where you have the liquid argon, but then you have a layer of gaseous argon at the top, which is used in the amplification of the charge. So there will actually be 4 modules, so that there's the possibility to build both single phase and double phase modules for DUNE. And these modules will be constructed in a staged approach, but the initial excavation will excavate caverns for all 4 of these at the site. Okay, so DUNE also will see a large number of these electron neutrino, electron antineutrino candidates. I think these plots show, right, this is 3.5 years each, so for 7 years of operation, they're collecting about 1,000 electron neutrino candidates. This is then showing, as a function of the true value of the CP phase, what level of significance they can detect CP violation at. So of course this goes to 0 for values where there's CP conservation. But for the 3 sigma level, for example, they can detect, they have sensitivity at 3 sigma for 75% of CP values after 10 years, which is similar to what Hyper-K has. This is also a plot showing how the resolution, so once again looking at how well the CP phase can be measured in the detector. You can see it evolving this is similar to the Hyper-K plot in that there's a line for when the true value is close to maximal CP violation and when the true value is at CP conserving value. And in fact, it looks like we're doing better in DUNE compared to Hyper-K. You can see here at the end of this plot, we're at 10 degrees here where we were at about 20 degrees in Hyper-K for this case. But it's a bit hard to compare because this actually goes beyond 10 years. So actually at 10 years, this is at about 14 degrees. But there's another effect going on here, which I'll put off till later to talk about, but it's an interesting effect. DUNE's real bread and butter for the neutrino oscillations is measuring the mass ordering. So with this 1,300 kilometer baseline, you can see essentially the range of oscillation probabilities you could measure for different values of delta CP in the normal hierarchy and in the inverted hierarchy. And you can see that these 2 bands are completely separated, and with the high statistics of DUNE, you can really tell whether it's a normal hierarchy and inverted hierarchy. So for all values of the delta CP, DUNE will make more than 5 sigma measurement of the mass hierarchy. So it'll really, if it's not already determined, DUNE will pin it down for sure. I also mentioned this question of whether the theta 2,3 angle is 45 degrees, so whether we have maximal mixing. So both experiments will make measurements of theta 2,3 with kind of similar precision and essentially be able to reject the maximal case or the wrong octant, where octant is this region above or this region below, with about the same sensitivity. However, these experiments, these measurements in particular, will be really sensitive to systematic uncertainties. So I want to revisit this issue of systematic uncertainties and how we model the neutrino interactions. So remember that we're working from a 6% error currently in T2K, and we need to get down to less than 3% for Hyper-K, and we have similar requirements for DUNE, so this is a real challenge. One of the approaches we're taking to address this is applying the so-called prism concept to really understand how we reconstruct energy in these detectors. So let me explain what we're doing here. So this is a plot that's showing the neutrino energy spectra in the DUNE beamline, but changing the off-axis angle. So essentially taking a near detector and moving the near detector from when it's on axis, which is this, to slowly moving it off axis. And you can see as you move the detector further off axis, you're measuring beams with lower and lower peak energies. So you can imagine that this is a way to really probe how the neutrino energy relates to what we observe in the detectors, because if we make all of these measurements, we have a large amount of information there. So we want to do, so this actual concept has been proposed both in Hyper-K as new prism and in DUNE as DUNE prism. And in Hyper-K, we want to move a detector vertically. In DUNE, the proposal is to move a detector horizontally. But I'll show the example of how this works in Hyper-K. So we have this detector. It's a water Trankov detector. You can see This is looking inside the tank of the detector where we have our photosensors. And this actually sits in a deep pit where the water level is adjusted, and we can move this detector to different levels in here, and each level is a different off-axis angle. So if we're at the bottom of the pit, we're measuring a much higher energy beam, and if we're at the top of the pit, we're measuring a much lower energy beam. So one of the ways that we can use the data from these types of measurements at different off-axis angles is to think about starting from a spectrum like this blue spectrum, which is in the hyper-K beam at 1.7 degrees off-axis. And essentially, we want to subtract away the high energy tail of this and the low energy tail. So we do that by going further off axis to subtract away the low energy tail, and further on axis to subtract away the high energy tail. And we can make a much narrower beam, which is this red distribution when we do that. And once we've made this rather narrow beam, then we can directly measure the resolution function of the detector. So we can tell for a given neutrino energy, here 900 MeV, what the reconstructed energy distribution is. So this is essentially directly measuring the resolution function. And this gets to this problem of how we reconstruct the neutrino energy in these events. Okay, so that brings me to the last topic that I want to talk about, which is another way to address systematic errors and also do more physics, and that's to put a detector here in Korea. So it turns out that if you take the J-Park neutrino beam and project it beyond Japan, somewhere in the middle of the sea, it comes out of the ocean and then continues on across the Korean peninsula. And in fact, if you think about sites located in this region, you can actually put detectors at positions where the off-axis angle ranges between about 1 and 3 degrees. And the baseline is about 1,100 kilometers, so not too different from the baseline in the DUNE experiment. So you might ask, well, what's the point if I'm going, the flux of neutrinos should fall off as r squared. So if I'm going so much further away, there are going to be a lot less neutrinos. Why would I want to put a detector here where the neutrino flux is less? And that is essentially so that we can study the second oscillation maximum. So this is the oscillation probability, this is the difference between the muon neutrino to electron neutrino probability and the muon antineutrino to electron antineutrino probability. So this is essentially the CP effect. As a function of energy for different baselines. So 300 kilometers is essentially the baseline for the detector in Japan, and this is the first oscillation maximum around 600 MeV, and that's what we're measuring. But if we go to a longer baseline at a similar energy, we're actually looking at the second oscillation maximum. And essentially the CP odd term that governs this CP effect has an L over E dependence. So as we go to the longer baseline at the same energy, we essentially get a 3 times larger CP asymmetry. So this is great. So even though the flux is decreased, we have a larger asymmetry, and in the end we get a similar sensitivity. So we looked at a number of sites in Korea and found 2 of them that were good candidates. One with an off-axis angle that's similar to the hyper-K detector in Japan, and one that's a bit more on-axis at 1.3 degrees off-axis. So actually at both of these sites, preliminary geological and surveys and construction cost estimates were made, and of course we've done sensitivity studies at these sites. So this is a plot that's showing the sensitivity for the CP violation discovery for 2 detectors in Japan versus a detector in Japan and one at the Mount Bissell site, and a detector in Japan and one at the Mount Bullion site. So what we see essentially is that even though we have fewer statistics with the detector in Korea, we actually get similar sensitivity, which is great. This is confirming that fact, and in fact we do a bit better. So you can see the configurations with the Korean detector cover a broader range here. So it's an improvement for the CP violation sensitivity, but it's also doing it with less sensitivity to the systematic uncertainties, which makes a more robust measurement. We do much better for the mass ordering determination. Particularly with the Mount Beasel site, so this is the site with the more on-axis beams, so the neutrinos are of higher energy, and that gives us more hierarchy sensitivity. This is without including the atmospheric neutrinos, but just the accelerator neutrinos, we already get to about the 8 sigma level for the mass ordering determination. And then I'm revisiting now this issue of the CP phase sensitivity. So this is for 10 years of operation with 2 detectors in Japan versus the configurations with one of the detectors in Korea. And you can actually see as we go to the Korean detectors, and especially to the Mount Beasel site, these regions are near CP violation, maximum CP violation, and we really get an improvement with the precision of the CP phase. So we're doing much better on the measurement of the CP phase. And in fact, we're getting similar precision to DUNE around 15 degrees after 10 years. And the other important point here is that once again, we're not limited by systematics in the detector, but we're limited by statistics, so we can operate even longer and improve. So you might ask why this is, so let me just give a brief explanation. If we revisit our neutrino oscillation probability, there's another interference term in this probability that depends on the cosine of delta. But importantly, it also depends on the cosine of delta m squared 3/2. So this term goes to 0 when we're at the oscillation maximum. But this term actually dominates the CP violation, or the delta CP sensitivity when we're near maximal CP violation. So to get the most out of this term, we want to actually go away from the oscillation maximum where this cosine delta m squared term is larger. And this is showing oscillation probabilities for different values of the parameters and the neutrino flux at the Mount Bolian site. And you can actually see that in this case, there's a lot of flux in between the first oscillation maximum and the second oscillation maximum, where we get the largest effect from this term, which is why we have the best precision on the cosine the delta CP measurement for that detector. DUNE gets a similar thing through its broadband beam, so it has a lot of events between the first and second oscillation maximum, and that's why the DUNE sensitivity is also looking better than just the single Hyper-K detector alone. Okay, so that brings me nearly to the end. So I just want to talk a bit about schedules. So this is the timeline for DUNE as shown at Neutrino 2018. As far as I know, this hasn't changed significantly. So DUNE has an approach actually of building the detectors, starting to build the detectors first before the beam is ready. So actually the first module will begin installation in the lab in 2022, but the neutrino beam will become available in 2026. So of course they can do physics with atmospheric neutrinos, proton decay search, all those other types of physics before the beam comes, but then once the beam becomes available in 2026, they start the long baseline physics program. This is a rather complicated schedule for Hyper-K. Some important points are that seed funding for Hyper-K was approved in 2019. So this is typical for large projects in Japan. There's usually 1 or 2 years of seed funding before the full approval of the project. So we're hoping that, and rather confident that Hyper-K will be fully approved this year. However, already the University of Tokyo has made a commitment to start the construction of the project in 2020. And then you can see with that plan, we get to 2027 where we're filling the tank with water and we start taking data. So the 2 experiments are starting around the same time. Okay, so that brings me to my summary slide. So I just want to reiterate that neutrino oscillations are interesting probe of what we believe will be new physics at a higher energy scale. And also a potential new source of CP violation, which is, really interesting. The past experimental program has delivered really robust measurements and Nobel Prize winning results, and we aim to continue this tradition. The current long baseline experiments are seeing hints of interesting results. So hints of CP violation and possibly maximal CP violation. And also it's starting to look, there's some global preference for the normal mass ordering. But to really pin these things down, we will need the next generation of experiments, Hyper-K and DUNE. that will make definitive measurements of the mass ordering and will really make our most sensitive searches for CP violation and the measurement of the oscillation parameters. And I think it's really important to point out that I think my opinion, and I think the opinion of many people, is that a detector in Korea should play a critical role in this program. It brings significant improvements to the sensitivities for the oscillation physics, and of course, a whole other set of physics that comes with such a large detector. So thank you.
To go back to the Korea neutrino detector with the delta CP sensitivity.
Yeah. Sorry, this one?
Right.
Yeah.
So if you compare this DUNE at the 10 years old version, are you assuming the 2.4 megawatt beam as well, or?
No, so here we've only assumed the 1.3 megawatt beam for the full operation time. So if we can, so there is the potential to increase the beam power at JPark even higher. Higher power would allow us actually to accumulate the data faster and do even better.
So that particular plot assumes that the current JPark beam power, and then comparing that with the formula 1.4 megawatt beam.
So sorry, this assumes that the JPark beam will be upgraded to 1.3 megawatts for Hyper-K, but it will stay at that value.
Okay.
The DUNE sensitivities assume that the beam starts at, sorry, I forget the number, 1.2 megawatts, and then is upgraded to 2.4 eventually. Sorry. Yeah, so DUNE starts at 1.2 megawatts and is upgraded to 2.4. So all the sensitivities shown for DUNE assume that upgrade of the beam power to 2.4 megawatts eventually.
Okay.
Any other questions or comments?
For you said that for the Korean neutrino detector to run for 10 years, and during that 10 years, for what? How many years do you assume for the neutrino, and how many years do you assume for the detector?
Sure, good question. It might not be obvious to most people from these plots, but right, so the anti-neutrino cross-section is about 3 times smaller than the neutrino cross-section. So to get equal number of candidate events in these two modes, we're running essentially 3/4 of the time in anti-neutrino mode and 1/4 of the time in neutrino mode. And that's what gives the best sensitivity for Hyper-K. So we've assumed that, since it's the same beam, we've assumed the same running configuration for the Korean detector.
You mentioned that DUNE has 1,300 kilometer beam line, and if you build a Korean detector, it has 1,100 kilometer, right? Then, if you see the number, what's the advantage of building a Korean detector compared with DUNE? I mean, DUNE has a larger beam distance.
Yeah, so the thing that I think the Korean detector really has is, let's go back to DUNE. The second oscillation maximum in DUNE is kind of barely covered by the neutrino flux at DUNE, and in fact, it's down here. And you have all of these events up here, and generally what happens when we reconstruct these events is they feed down in energy. So you're really dealing with large backgrounds at the second oscillation maximum that come from higher energy events. I think the real advantage with the Korean detector is that the flux that we have is much better tuned to the second oscillation maximum. So you can see, even in the Mount Biso case, the flux is really, the peak of the flux is really close to where the second oscillation maximum is. So we get a lot more statistics there. And if we really want to understand physics at the second oscillation maximum and confirm that what we're seeing is really consistent with what we expect at both the first and second oscillation maximum, then the Korean detector is the way to go.
Any other questions or comment? So I have one question. So for the case of DUNE, you have a higher neutron energy beam, and after scattering, this nucleon maybe broke up and produce a more complicated final state than the hyper-K. So isn't that, so this is well understood, this part?
No, I mean, I think that's definitely, sorry, I have to go way back for that, but that's definitely what this issue is getting at. When you try to do this calorimetric reconstruction, you have to know, well, these remnants coming from the nucleus, what the efficiency for those particles are, how often you detect them, and how much of the energy you reconstruct for those particles. And that's a real challenge. There are similar challenges in the water Trankov detector, because there we assume quasi-elastic scattering, but there are other processes that look the same. So this really is just a problem in both experiments, even though it shows up in different ways. But the one thing you do try to do with the liquid argon detector is measure as much as you can of what's coming out of the interaction.
Yeah, I have a question. So it's about timeline. So it seems to me that the DUNE has a clear timeline, assuming there is no major accident. So to me, in order for Korean detector to make sense, there should be certain kind of timeline to compete, right? So how many years, I mean, when should it be beginning taking data in order to compete?
Sure. So I think it depends on what physics you're interested in. So if you just care about the mass hierarchy, yeah, if DUNE starts running before the Korean detector, DUNE will probably make a 5 sigma determination first. So it's nice to confirm it here, but it won't be the first to get to it. If you're talking about the precision of the CP phase, that's an experiment that's a measurement that you just need as much statistics as possible. So it's really a long-term measurement. So if you start a couple years later in the Korean detector, it doesn't necessarily mean that you're not competitive there. So for this, I think you can start a bit later. And in fact, I think the advantages of the Korean detector will make this, in the long term, the best way to do this measurement. Same thing for the CP violation discovery. So it may be that the CP violation is really large, and anyway we find it quickly. But if we do end up in these regions where the CP violation is rather small, then it's going to be really hard to measure it without running into the limits of the systematic uncertainties. In that case, being at the second oscillation maximum will be critical, because then the CP asymmetry is 3 times larger, and we won't be dominated by the systematics. We'll be dominated by statistical uncertainty, and we'll be able to go with more running and higher beam power to even more sensitive searches if we end up in this region.
Does that mean wait and see then? Is this essentially, from the Korean perspective, should it be?
No, I don't think it should be wait and see. I think it should be try to do it.
Create money now.
Yeah. No, I think there's a step that has to happen first, which is we need full approval of the project in Japan, because anyway, there's no reason to put a detector there if there's no beam from Japan. But my personal opinion is that once that happens, we should try to push it as soon as possible.
So what you're trying to say, I want to make you understand, the one detector choice in hyper-K is comparable with the DUNE with the broadband DUNE program. Is that?
I think the answer is that with one detector, if CP violation is large, hyper-K will find it first, because hyper-K will accumulate statistics very quickly. For things like the CP mass hierarchy, DUNE will do it faster. And precision measurement of the CP phase, once again, it depends on what the true value of delta is. But that's an area where I think it would be better for Hyper-K to have the Korean detector to be competitive with DUNE. Although I will say that DUNE sensitivity studies don't really have full systematic error models in them yet, so I don't know how much to trust that. But so Hyper-K is relatively competitive, but I think there are potential advantages that DUNE has there that would be made up for by having the detector in Korea. And of course, the broader physics program, proton decay, supernova, neutrinos, my personal opinion is that that's where Hyper-K also really excels, because you have this order of magnitude more mass. That extra mass is really what you need to get to interesting results in proton decay, or to really start to get interesting samples, for example, of the supernova relic neutrinos. So to me, that program is also quite important and really motivates Hyper-K.
Okay, although there may be more questions, this is the time to move for the next talk. So let's thank Mark again.